I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for the.
A lot to cover today. Again, round of applause for DD Cash. I should have asked you before, how's your money situation?
It's getting better.
Getting better? Okay. I mean, again, we pay you here. I know your radio show doesn't pay you, but you're still doing gigs with private party stuff.
Here and there.
So, why do you want money so bad?
Yeah. So I had some crypto scheme going on.
Okay, that's stupid. Yeah. Okay. Yeah.
Yeah.
Do you lose all your money on that?
Just recouping.
All right. All right. Blockchain and crypto is a scam. Blockchain is a terrible implementation of our database. We'll see that after the fall break when we talk about transactions. Don't do that. Oh, well, that's his problem. Whatever. All right. For you guys in the class, again, next class, this room, same time, we'll be having the midterm exam. The study guide is online. The materials online on Piazza. Everything, all the notes are posted. Homework 3 solutions went out this morning, so you can check that as well. You need to bring your CMU ID. If you want to do logarithms, you can't do them in your head, bring a simple calculator. Your phone is fine. And then a single page, double-sided handwritten notes. Again, the idea here is, again, forcing you to look through the material and write down what you think is important, rather than just trying to take every single slide and make it a microfiche and try to shrink it down as small as possible. Yes, in the back. Yeah, if you use a basic calculator on the phone, that's fine, yes. Because most people don't have a regular calculator these days. And then because my office hours are after class on Wednesday, plus I got to go travel, I moved my office hours to be tomorrow in the afternoon at 4:15. I'll post those in Piazza as well, okay? So at least if you want to talk to me, you talk to me before the midterm. Any questions about the midterm? Again, it's chapters or the lectures 1 to 11 inclusive. So today's lecture and joins is obviously not going to be on the exam. All right, and then project 2 is out. The recitation for that will be also Wednesday after the midterm, because I assume no one's going to look at it until after midterm. So that'll be 8 o'clock this Wednesday on Zoom, and then we'll post the materials afterwards on Piazza. Yes. The question is the real exam going to be like the practice exam where the questions are all what? Sorry. Yes, roughly multiple choice. But some of them you could some of them will be if the multiple choice question isn't there, you can then fill in something else. But it'll look like that. Okay. All right. Again, if you can't get enough about databases, if you're addicted like I am, we have much more database talks coming up. Today's talk will be at 4:30 p.m. on Zoom. That'll be from the co-founder, MotherDuck. The guy also was an engineering director at SingleStore, and prior to that, he was also engineering director or lead developer at Google, working on BigQuery. And sort of the story of MotherDuck and DuckDB is, from this guy's perspective, which I agree with in some ways, that instead of building this massively distributed database system, if you make the single node be as efficient as possible, then that can take you pretty far. So MotherDuck is sort of pushing that story. Then next week, we'll have the SpiralDB guys give a talk about Vortex. Vortex is a replacement for Parquet. And then after that will be the guys from Columnar. These are people that used to work on, or do work on Apache Arrow, which is something we'll talk about when we talk about distributed systems. But it's an in-memory representation of data, sort of like Parquet is for files on disk. Arrow is for in-memory stuff, so you want to pass data between different systems. They speak Arrow, they're compatible. And so Columnar is a commercial sort of expansion of the project. Okay? All right, so today's lecture is going to be awesome because it's about joins, and this is going to be for single node systems like DuckDB. This is where most of the time is going to be spent running your queries. When you go to distributed, it's going to be the shuffle operator, which we'll cover that later. But on single node systems, joins is the most extensive thing, so we want to see what we can do to speed that up. So last class, we talked about how to handle sorting, and we made this emphasis on that if the database doesn't fit in memory, the data you want to sort doesn't fit in memory, then you would use a technique like external merge sort to allow you to write sequential files out the disk, read sequential files back in, and still perform the sorted operation. And the high-level design pattern that we took advantage of in sorting, and we'll take advantage of today again in joins, is this divide and conquer approach. By taking a large problem, breaking up into smaller subproblems, solving those each individually as efficiently as possible, and then putting the result back together, right? And the way that the two-level strategies we're going to use for both sorting and hashing and aggregations that we saw at the end of the last class as well is either sorting or hashing. The nested loop join would be like the dumbest thing you can do because it's just for loops. But with sorting and hashing, again, these are a bit more sophisticated and under the right conditions can do much better than a bunch of nested for loops. All right, so sort of goes without saying, because you did homework 1 about why we would need to join. This will be the one slide that I pretty much only mention normal forms this entire class, entire semester. We used to teach it in the older versions of this course, the normal forms and Armstrong's axioms and all this stuff. But like in the real world, nobody uses them. And if you just use like if you write something in Ruby on Rails or Django or pick your favorite object relational map or ORM, you basically end up on third normal form, and that's good enough. So I just want to mention that these normal form things exist. You don't need to worry about them. And then if you only end up building a query optimizer or do other more sophisticated things, you may have to care about them. In the real world, you don't need to know them. It's basically just saying that it's a way to break up your tables into smaller tables or combine them based on some properties that you may care about. So first normal form would be like, if I take my database of all my students enrolled in classes and their grades, I can put that in one giant table with all the columns put together. That's called first normal form. And obviously that's going to be very inefficient because it's duplicating a lot of data. So you start breaking them out to like the students table, the enrolled table, and the course table, right? That ends up being in a higher normal form, and it's a naturally way to represent data. So the reason why we need to do join is that if you start breaking your tables up from the first normal form with this one giant universal table into these separate tables, then I want to put them back together to get back the original data. That's what the joins are going to do for us. And so we want to have a join operator in our system that can reconstruct us back to the original data that we want without losing anything. Seems sort of obvious, but that's what we care about. So the join algorithms we're going to focus on in this class today, in this semester, are going to be doing what are called echo joins or inner joins. And we're going to do this on doing binary operators, meaning taking two tables and joining them together. Because this is going to be the most common join operator that will be executed or used in a database system. Right? Taking two tables, just joining them together based on something equals something. Something in the first table equals something in the second table. That's the most common thing, and that's what we want to focus on. Right? And then we can tweak these, this is the basic algorithms we'll talk about today, to handle other things like left outer joins or full outer joins, or doing like anti-joins, or like I want to see something doesn't equal something is not in the table, join those together. So all the algorithms we'll talk today can be used for handling these other type of joins. They're called like theta joins. But again, we don't have to worry about that. There are algorithms to do what are called multi-way joins. So if I have more than two tables in my query that I want to join together, there are some algorithms that can try to join them all at once. But typically this is very hard to do. Microsoft had this in SQL Server in 1998, but then they took it out 3 years later in 2001 because the performance was not that great. Sometimes it'd be really fast, and sometimes it'd be actually worse than doing a simple binary join. So most database systems you know about, Postgres, Oracle, MySQL, pick your favorite, they're going to be doing binary joins, taking two tables and joining them together. There's another class of algorithms, or modern variants of these multi-way joins, called worst-case optimal joins. We're not going to cover that this semester. You don't need to know that for this class, but these are algorithms that can do like three-way joins very efficiently, and this is useful when you're like doing graph traversals in a relational database. Because when you join two tables, the size of the output of the join is be much, much larger than the original inputs. And then you do another join to reduce it down further. Think of like doing a bunch of self-joins. So we'll cover worst-case optimal joins in the advanced class. Most systems don't actually support this. The relational AI guys that came a few weeks ago, they're one of the systems that support this. The Germans support this. But pretty much all the commercial systems don't do this. So we don't need to worry about that. All right, so in general, the rule of thumb we're going to have in all our join algorithms that we talk about today is that we're going to have two tables, right? We'll have the left table and the right table, or the inner table and the outer table. And we're always going to want the smaller table of the two tables we want to join. We're going to want to put that as part of the outer table in our query plan. And we're not talking about query optimization just yet. We'll talk about this after the fall break. But it's the database system's query optimizer to figure out which of the two tables are smaller and make sure we put these things in the right order. And again, these algorithms today, again, are binary join algorithms. So taking two tables, joining together. If I have more than two tables I want to join in my query plan or my query, then the optimizer also can try to figure out what the order I want to do the join. So I join A and B first, followed by C, or B and C first, followed by A. And the way it's going to try to figure this out is based on some statistics that it's going to collect about the database system, about these tables, to try to make educated guesses on the right way to execute things. But again, for this class today, we don't need to worry about. We're really focused on what's the algorithm we're going to use to join the tables together. All right, so we saw this query plan last time, right? And we said that the representation of a query plan is basically going to be either a tree or a DAG, and a tree is a subset of a DAG. But the idea is that we have data at the bottom from our source data for the tables or files or whatever it is. We're going to be feeding that up into the query plan for other operators to do whatever it is, the computation they want to do, and then produce a final output that's in the root that we then send out to whoever's requested it, either a client or writing it to another table, whatever you want, right? And so we'll discuss after the fall break, we'll discuss how to, what this data is going to look like. Is it going to be a single tuple, a batch of tuples, and so forth? And again, we'll worry about that later. But for today's discussion, we need to talk about what the output of these join operators is going to look like, and then how we're going to determine whether one algorithm is going to be better than another. Right? How's the database system going to say, I want to use a sort merge join over a hash join? And again, that's going to then feed into the optimizer when it's try to then figure out, oh, I want to join table R and S. I want to use this algorithm. I want to use that algorithm. But for us today, we're not worried about that decision yet. We just want to know is how to determine whether one algorithm is going to be better than another. So for the first one, the output, again, when we do a join, the basic idea is that taking a tuple from one table and a tuple from the other table that are getting matched on some join key, and I want to then mash them together into a single new output tuple, right? And so what this output is going to look like is going to depend on a bunch of different factors of how we're actually implement our system. But we already saw a little bit of this last class when we talked about the difference between early materialization and late materialization. And now, again, when we talk about sorting, but now in the context of joins, this is going to matter because now we're going to assume the data that's coming out of our join operator is going to be used by another operator in that query plan or produces the final output. So we need to decide what this should look like and how do we pass data along, or whether to pass data along or not. So again, early materialization is that the idea is that all the data we're going to need to do the join or anything else in the query plan is going to be given to us or fed up to us from the bottom in the leaf nodes, right? So now if I'm joining tuples from R and S, the output tuple is going to be a concatenation of all the tuples from R, all the attributes from R, all the attributes from S, and then we'll just mash them together and stitch them together like this, right? So that's what'll get passed up as we do this, after we do this join. So I'm feeding tuples up from R, feeding tuples up from S. Again, I do a filter, but then if I match them on the join key where RID equals SID, the output result is going to be, again, all the columns of R for all the columns of S stitched together. And so the advantage of getting early materialization is that we never have to go back to our base tables, R and S, to go get more data because everything's being passed up to us from the leaves. And then recall that late materialization is that instead of passing up data, we're actually just going to pass up the record ID. And then the bare minimum we need to actually do the join. So maybe it's the columns that are being used in the join predicate, join expression. So in this case here, I have the RID and then the SID because that's what I'm trying to join on in my on clause in my query. And then instead of having all the extra attributes for both these two tuples or for these two tables, I'm just going to have the record ID. And then I do my join, mash these guys together, and then that's what gets passed up. And then now with late materialization, the problem is, or the challenge is going to be that at some later point in my query plan, I need another attribute from table S, and that's not going to be passed along in the tuple that's coming as part of my output of my join. I gotta again go down, make a call down to whatever this base table is, and go get that data, right? So the advantage of this in the context of column stores, where joins are I'm not saying they're not that it's not that they're more common than OLAP queries, but in the OLTP workloads, but in OLAP queries, you usually end up joining more tables than you would in an OLTP system. So again, in the column store system, I didn't have to go read the data from the other columns that I didn't need to do my join. And furthermore, if my join is very selective, meaning I'm throwing away a lot of tuples because they're not matching my join clause, then I'm going to have a win because the number of tuples I'm going to be passing up is quite small. Then who cares if I have to go then fetch the remaining data that I need from the columns that I didn't pass up, because these guys down here could have been a billion tuples, but I ended up with 2 after the join. And so therefore, it's not a lot of data I have to go read to go complete the query. Again, the main thing to understand from the join algorithm is that we're going to take attributes from one table, attributes from the other table, and they'll get matched together. And you'll have to pass along the join key in order to compute that join. But whether or not you pass along the other attributes depends on the system, or whether you're implementing late materialization or early materialization. All right, the other thing we need to, again, to determine whether one algorithm is better than another is the cost. So unlike in, I guess, your algorithms class, it's usually like, the complexity defined in terms of like the number of times I have to do a certain operation, in the actual computation itself. For us, when we do joins in this class, we're going to focus on the amount of I/O I have to use for both reading and writing data. If I have to spill things to disk and write it back out, I got to keep track of those costs. And if I got to read it back in, I got to keep those costs as well. Right? We saw this again with the sort merge algorithm from last class. So for today's lecture, we're going to assume that we're going to be joining tables R and S. And we'll say that for table R, it's going to have big M pages in the table and a total of little m tuples in the table. And then we'll have the same thing for S, with big N for the number of pages and little n for the number of tuples, right? For this class here, again, we're only focusing on disk I/O because that's going to be the slowest thing for us. Therefore, we're going to ignore the cost of actually doing the actual join itself. Like if we build a hash table, we're ignoring that cost. We have to probe the hash table, we ignore that cost. Last class we talked about comparing keys in the sort algorithm. We'll ignore that cost as well because the disk I/O is going to be super expensive. We're also going to assume that everything's going to fit on a single machine, and therefore we're not worried about sending data over the network. When we talk about distributed databases, then that all comes back. The network costs become a big part of the cost, right? Because now you may be sending things across the world, and that's super expensive. But again, for this class here, we're just going to focus on disk I/Os. So for all of these algorithms as well, we're also going to ignore the cost of the output of the operators, because they're going to be the same for one algorithm to the next, right? Because I have my hash join algorithm and my nested loop join algorithm. They're all going to produce the same logical result. It might be sorted in a different order, but again, relational model is unsorted, so that's okay. But the number of tuples going to be passing up is going to be the same. So we'll ignore that cost as well. All right. So I sort of already said this, but it's obvious as well. Like again, the inner join is the most common thing we want to do. Common join operator we want to do in our database systems. So we're going to spend a lot of time to make that as efficient as possible, and that's what this class is all about. Sometimes you see some systems also support cross joins. There's not really much you can do to make these things work efficiently because it's just 2 stupid for loops. You're just taking all the tuples from one table and mashing it together with all the tuples from the other table. Building a hash table or sorting things ahead of time doesn't help you in any way. You obviously can batch things to reduce the number of times you got to go back and fetch data, but at the end of the day, there really isn't anything you can make that work really efficiently. So again, we're just going to focus on doing the inner joins because that's the most common thing, and there we can do some techniques and some tricks to make things run faster. All right, so here's the menu for today. We're going to go through the most basic algorithm, the nested loop join. This is what most people build first when you build a database system that needs to support joins. We'll talk about 3 different variants of this. Then we'll spend a little time talking about the sort merge join, but then we'll spend most of our time talking about how to do hash joins, because hash joins are going to be the most important join operator you can have in your system. And this will be what, if you want your joins to run fast, you'd want to build this first before sort merge join. All right. All right, so let's look at what I'll call a naive nested loop join. And this is sort of a way of like, this is a straw man to say why, here's a bad way to do a join, and then we'll see how to build upon this and make this run faster, right? So we're going to generate a join table RNS. It's called nested loop join because the actual implementation of this algorithm is just a bunch of nested for loops, right? So for every single tuple in R, we're going to go get every single tuple in S, check to see whether our join keys match. If yes, then emit it as part of our output. So the parlance we'll use, or the vernacular we'll use for when we talk about joins is the inner table and outer tables, and this comes from these nested for loops, right? So we'll say the outermost for loop is called the outer table, and the inner one, the one in the middle, is called the inner table. So even though people, even for like a hash join algorithm, sometimes it's not going to be doing nested for loops, but people still maybe refer to these things as the outer table and the inner table. And in most diagrams of query plans, the outer is on the left, the inner is on the right. Some systems, I think Snowflake reverses it, right? Just there's not like a specific term, like specific way to say like within a diagram, this is definitely going to be the inner versus the outer. Different systems for whatever reason do different things in their visualizations of query plans. So again, I've already said before, I've already said this just now, like this is bad, don't do this. Why is it bad? Why is it stupid? What's that? He says quadratic, yes. The IO, absolutely yes. So this is like stupidly naive, right? This is just saying for every single tuple in R, scan S in its entirety, get all, go get every single tuple in every single page, read it again, and then get the next tuple in the outer table in R and do the exact same scan all over again, right? It's naively stupid and it's super expensive. So in this case here, would be the cost would be big M plus, so the big M is for the scanning all the pages in the outer table. And then for all the tuples in the outer table, I got to scan all the pages of the inner table. So little m is all the tuples in the outer table, and then big N is all the pages in the inner table, right? So if you just put some numbers to this, you'll see how terrible this actually is. Again, this is like the dumbest thing you could ever actually do, right? So if our table is kind of small, right, it has 1,000 pages in R with 100,000 tuples and 500 pages in S with 40,000 tuples. If we didn't plug and chug our numbers in, we end up with us having to do 50 million IOs. And if we actually put a wall clock time and say how much is the cost for a given, for one IO, right? This is running on SSD in a local box. It's 100 milliseconds is reasonable. It's slow, but it's a ballpark number, right? Just joining these two tables, if you just go fetch every single page and ignoring like hardware caching or OS caching, anything, just if I have to go pay the cost of going fetch every single page for the inner table for every single tuple in the outer table, it'll take 1.3 hours. All right. So remember I said before that in general, we always want to put the smaller table as the outer table. So in this case here, the smaller table is S, that has fewer pages and fewer tuples. So I just switch the order of them, right? And now plug and chug, I got the time down to 1.1 hours. So, I saved 20 minutes, but it's still not that great. So in my example here, these two tables are ridiculously small. Assuming I'm doing 4 kilobyte pages, then the size of this one example here is 6 megabytes. Like that'll sit easily in your L3 cache. You don't have to go to the disk, right? You could easily do this join entirely in CPU cache land. And that's going to be really fast. But if I have to go pay that disk IO cost, if I'm naively getting every page of the inner table for every tuple in the outer table, it's going to be horribly, horribly slow. So this is like the dumbest thing you can do. But let's see how we can actually make this a little bit better. So one simple thing is to do what's called a block nested loop join. And this is, again, because we know our tuples are not just sitting by themselves on disk, they're in pages with other tuples that they're friends with, then when we go fetch a page, we want to do as much processing with all the tuples in that page before we move on to the next page. So we just changed now our 2 nested for loops to be 4 nested for loops, where for every single block in the outer table, go get a block on the inner table, and then every single tuple in a block on the outer table, do the join against all the tuples in the inner table. Then we can do a little bit better here, right? So now our cost is going to be m plus big M times little n. Again, big M is the cost of scanning all the pages in the outer table, but now for every single page, for every single one of those pages in the outer table, now we're doing a scan of all the pages on the inner table, rather than doing it on a per tuple basis. Now our cost can be reduced quite significantly, right? So again, this question, yes? This question is, for every single big M pages in the outer table, scan all the pages in the inner table. Yes. Yes.
So it's not asymptotically better, it's just better cache.
The statement is, and they're correct, that it's not asymptotically better, it's just in practice, the constants are better. Yes, I said this earlier. Constants matter in database world. So again, we want the smaller table to be always on the outer table, and we would determine whether which one's smaller than the other, not based on the number of tuples, but rather based on the number of pages, because that's the main cost for us of going to disk, is going fetching pages, not going fetching individual tuples. And obviously in this scenario here, I'm assuming I have only 2 buffer pool pages to store data. In a real system, you would have a lot more, right? So in this case here, you want to try to store in a sort of in a block nested loop join where you have multiple pages you can use to store the data as you scan it. You want to put as many buffers from the outer table in memory as possible, and then just leave one page for the input for the inner table to bring one page in, and then another page to write the output after you do the join, right? So it basically looks like this now. For B minus 2 pages, B is the total number of buffer pool pages I have, scan all the data I can from R, and then go fetch each individual page from S, and then just do that scan of the join of the tuples in the 2 inner for loops. Yes?
Could emit up to also combine the 2 pages of data?
The statement is, I could emit also B minus 2 pages of data, but like I can only, in this sort of simplistic example, I'm going to fill up one page, write that out, then fill the next one up. Yeah. Yeah, you can do asynchronous I/O, and therefore you need more. Yeah, keep it simple. Yes. All right, so if we go back now to our formula, okay, assuming you have B minus 2 pages for scanning the outer table, now our cost is going to be big M, which is again scanning the outer table at least once, and then I can get for every M divided by B minus 2 and take the ceiling of that. For all those sort of batches of pages on the outer table, I got to scan all the pages on the inner table. And then chugging now with our simple formulas we had before, assuming that we have if everything can fit in memory, we can get this down now to do our the join of R and S from our simple example before, down to 0.15 seconds, so 150 milliseconds. So just by batching things up and taking advantage of the memory that's available to us in the buffer pool, we went from 1.1 hours to less than a second. Why is it M plus N? Sorry, well, because everything fits in memory. Then I read it all once, everything fits in memory, and then I just join it. Why is it not the constant above? Because the ceiling M divided by B minus 2, that's if I'm sort of have a batch where I'm reading things in, and then for that batch of the outer table, scan the inner table. If I can fit if all the pages from the outer table and the inner table fit memory, just scan it all. That's the M and the N, add it together, and just do the join on that. So what I'm trying to point out here is, even though the nested loop join seems kind of brain dead and stupid, if everything fits in memory, maybe everything's already is in memory, this is actually pretty fast, right? And we'll see when we talk about hash joins, there may be the cases where you do some of the join will be done sort of using the hash join with building a hash table, but the other and a small portion of it could be used using this sort of in-memory nested loop join, because you can rip through it pretty fast. So now, if I only have b minus or b equals 102, then I can get this down to 6,000 IOs, so about 600 milliseconds. But then if I again switch the outer to the inner one, make sure the outer table is the smaller one, then I can get it down to 5,500. Yes.
If oil relations fit in memory, then this isn't that much different from the version, right?
Then what? Sorry.
The performance is not much different from the naive version. It's just that it's just whether you get to use your cache, like CPU cache or not.
Yeah, their statement is, and they're correct, that if everything fits in memory, is it just the naive nested loop join? Yes. And if everything's in memory, that's fine. And so when we talk about the hash join, one of the approaches will be to divide and conquer. We'll split things up in such a way that we can maybe try to keep everything in memory, and then the naive nested loop join will work the best. If I have to go to disk, it's terrible. If everything's in memory, then I'm great. All right, so why is this so bad? Because we already said this. Again, if I had to go from disk, then I'm basically doing sequential scan over and over again on the inner table to try to match things from the outer table. So you may say, all right, well, sequential scans are not great. We spent a bunch of time learning my indexes. If I have an index, can I take advantage of that to make so that inner for loop on the inner table, make that go faster? And the answer is yes, we can do this. Some systems like Zero Server we talked about before, well, if you're doing a join or any kind of operation on a table, and if the optimizer realizes, hey, it'd be really nice if I had an index for this table, it would make my query go faster. It'll build that index for you, do whatever it is the operation you want to do in your query, and then immediately just throw it away. And then also give you back warnings and say, hey, look, I keep building this index or this table for your queries. It'd be really nice if you tell me I can have it for good and keep it around. And then the human has to decide whether to do that or not. All right, so if you have an existing index, then you can modify the nested loop join algorithm to do what's called an index nested loop join algorithm. All right, and it basically is now the outer table, you're still scanning through all the tuples. Then for the inner table, I'm going to take a key that I extract from the outer table tuple and then do a probe into whatever the index it is that I have available to me, and then see whether I have a match. And that's essentially doing the join for you. So the cost for this is hard to define because it's obviously going to depend on what your index is, like what data structure it actually is, and the size of it. So in general, though, we would say the cost now is going to be big M, because again, we always have to scan all the pages in the outer table. And then for every single tuple in the inner table, every single tuple in the outer table, we'll do some kind of probe into this index to again find a match. And again, we can't define this C easily because in this class here, because it's going to depend on a bunch of different factors that can vary from one index to the next, right? Whether it's a B+ tree or a skip list or a trie or a hash table, right? But this is basically what the hash join is going to do, right? So in this case here, assuming I have a B+ tree, I could probe in that and use that to make a nested loop join, index nested loop join. The hash join basically says, I don't have an index, so let me build a hash table now, and then do the same kind of probe like this, and then throw it away when the query is done, the same way that SQL Server does. Okay? All right, so the main takeaways for the nested loop join, if everything's in memory, it's going to be super fast, and that's going to actually be preferable in many cases. But in general, if we know we have to go read from disk, then I'm going to want to make sure the smaller table is always going to be the outside. Try to batch as much as I can on that outer table as I can in my buffer pool, because that'll make things go up, make things run faster. Okay. So the next join algorithm we're going to talk about is, again, sort merge join. And this is going to be built upon the external merge sort, or the sorting stuff we talked about last class. And as I said before, since the 1970s, it was just back and forth between in the research literature about whether sorting algorithms were better than hash-based algorithms. And then originally sorting was faster because the computers were really slow and hashing was really expensive. And then hashing algorithms got better, but then the hardware got better and sorting got better. It keeps going back and forth. But in general, the hash join is going to be preferable over the sort merge join. But you'd still want to have a sort merge join because if your query the data is already sorted on your join key, or there's an order by clause where you need to sort the data, you can kill two birds with one stone by doing this algorithm and producing results that are sorted for you. All right, so sort merge join has two phases. And again, the confusing thing about this is that last time we talked about the external merge sort algorithm, and we're going to use that external merge sort we can use that external merge sort for our sort merge join algorithm, and we'd use that external merge sort as the sort phase in our join algorithm. And then the merge phase in the join algorithm is different than the merge phase in the sort algorithm. Right? I'm not trying to confuse you. I'm trying to say, like, we can still use this external merge sort, which has its own two phases, in our join algorithm, which is going to have its own other two phases. All right? All right, so the basic idea is that we have our two tables that we want to join, and we're going to sort them based on our join keys. And then we're going to have, and that's what you do in the first phase. Then the second phase, you have these cursors that are going to walk through your sorted tables and start comparing across to see whether you have a match. And if you do, then you emit them as part of the join output, and then you just keep moving the cursors forward, marching through, and producing results. And the advantage, because the data is being sorted, at least in the outer table, you won't have to. The outer table, you won't have to backtrack up in the sort of results to look at tuples over and over again. In the inner table, you may still have to do that, but again, it's a simple trick to keep track of these things. But the sorting allows us to identify that we know there isn't going to be any match at some prior point in the table once we reach a certain point with our cursor, because the data is sorted. We can't see magically a value that should appear up above down below us. In the back, yes. The question is, can I explain an example where you have to backtrack? Yes. Let me give you a demonstration. Yes. All right, let me just skip this. This is the algorithm. Again, I don't like to show code in class, but basically there's two cursors. You scan through until you reach the end, and then there's logic to say whether one increments versus the other and whether you need to backtrack. Let's go through an actual example. So here we have our two tables we want to join, the R and S. And so the first phase of the sort merge join algorithm is to just sort them. So we want to join on the ID column. So in both these tables, we're just going to go ahead and sort them. Then now when we enter the second phase to do our merge, we're going to have these two cursors that are going to start at the beginning of their two sorted tables and start comparing with each other on the join key to see whether we have a match. And to handle backtracking, we're also going to keep track of this last value that says, here's the last value I saw when, as my cursor on the inner table moves down. So that way, if we then see a join key on the outer table that could have matched something up above in our inner table, we know how to go back and start the scan on that again. All right, so we start at the very beginning. Both two cursors are pointing to the first tuple. The join key is based on ID. So in this case here, 100 equals 100. So this is a match. And we just produce our output like that by just, again, mashing the two tuples, the attributes from the two tuples together. Now in this case here, because we have now a match, we're going to just move the inner table's cursor down by 1. And we leave the outer table's cursor where it is. Then again, now we do a comparison. 100 equals 100. We have another match, and we produce that as an output. And then now we're going to move down forward again on the inner table. But now at this point here, the value that we're looking at is different than the last value we just saw. So we got to record that this is the last value that we saw. So we saw 100 before 200, so we keep track that we have 100. All right, so now at this point here, 200 is greater than 100, so we know that we need to move down the outer table's cursor by 1. because at this point here, there isn't going to be another value on the inner table that could match with 100 where the outer table is pointing at. So we move the outer table's cursor and not the inner table's cursor. So that comes down here. Gets 200. Again, 200 equals 200, so we have match. We produce our output. Again, and then we move the inner table down. Record that the last value that we saw was 200, because now we're seeing 400. And again, 400 is now greater than on the inner table. If 400 is greater than 200 on the outer table, so we're going to then move down the outer table's cursor down by 1. Now we see 200 again. And we check our last value. We see that, oh, we just saw 200 before we got to 400. So now we know we need to backtrack and move the inner table's cursor back up to where 200 was, so that we can essentially restart this process of scanning the data in the inner table for the new tuple on the outer table. So then now again, we have another match on 200. We move the inner table down by 1. Now we get 400. This scans down, we get 300. 300 is less than 400, so we know we want to move down the outer table cursor, because there isn't something we can match here on the inner table, because we're already at 400. And because things are sorted, we know that we're not magically going to see a 300 later on, because it would have appeared before we saw 400, which we didn't see that. So we move the outer table down by 1. Now we have a match on 400. That's good. Inner table moves down by 1. Now we have 500. Keep our last value as 400. We're pointing at 500, though 500 is greater than 400, so the outer table moves down. Now we have 500 again, and that's a match. And now the inner table's cursor reaches the bottom. We still got to keep track of the last value for ourselves, right? Even though we reached the bottom, because we don't know what we're going to see. We might have another match on the outer table again. But now we get 600. 600 is 600 is greater than 500. So we know at this point we can short circuit, because there isn't anything that we'll ever see that will match between these two joins. So we can just scan through and just say we're done. Just finish up. Questions? Yes.
So the only reason we keep this last value and go back up is because multiple tuples from the second table can match with a single.
Yes, and the statement he made, and he's correct, is that the reason why we keep this last value is because there may be multiple tuples in the inner table matching with a tuple on the outer table. Yes. Now, you can be smart about it and say, oh, if I'm doing a join on columns where they're unique column or primary key, then I know that I won't have duplicates on the inner table for any match on the outer table. So in that case here, you don't need to do any backtracking at all, right? Be able to know that, therefore you have to maintain this. The question, what if there was 2 100s? So going back up here. Oh, so so in that case here, you'd have to keep track of so if you have 2 100s, so you see first 100 here, so you do this, you would scan through, you would match that, that's fine. And then now the inner table would come down, you would keep track of your last value as 100. The outer table moves down, it would see 100 again. At this point, it says, oh, okay, well, that was my last value, so let me backtrack the inner table. I don't have to backtrack on the outer table ever for this.
And when it backtracks, it goes back to the very first one.
Statement is, and they're correct, when it backtracks to the first 100 where this was. I'm not recording the pointer, but it would keep track of that. And again, if the worst case scenario, if I only have one value in this column when I'm joining, then I'm backtracking to the very beginning. But again, there's no algorithm to make that work great. Yes.
One of your joint condition isn't like a simple equal on.
Right. I was trying to avoid that. So the statement is, and he's correct. Well, this is an equality predicate, like equijoin. What if it's not that? Then you have to have additional logic to keep track of could I see something based on my join predicate? Is something going to be above or below me? It's more complicated, but yes, you'd have to do that.
Could you figure out something in all cases?
The question is, could you figure out something in all cases? What do you mean figure it out? What do you mean?
Figure out some way to do the submerged join for all sorts of joint conditions.
The question is, could you figure out a way to do sort merge join for all join conditions? Yeah, no, you can do it for all of them. I'm saying the logic of backtracking is just way more complicated, right? Other questions? That's a nice way to end it. That's nice. Yeah, good. Okay. So, all right, so what is our cost for this? Well, again, we have two phases, the sort phase and the merge phase. The sort phase cost is whatever our sort algorithm is going to be for both the two tables. So if I'm doing the sort merge join from last class, then it's the 2m times everything else there, because again, b-1 buffer pages. So I have whatever my cost is for sorting those two input tables. And then now the merge cost, without any backtracking, is just reading all the pages for both the inner table and the outer table once. Backtracking complicates things because then you'd have to know the distribution of the keys and how many duplicates you're going to have per key. So we can't obviously put that in our formula here. And this will be one of the recurring themes when we talk about query optimization. They make a bunch of assumptions of what your data looks like because it simplifies these formulas. Because otherwise, how could you know? So if I go back to with real numbers, again, sorting these two tables here, assuming I have 100 buffer pool pages, then the sort cost for table R is 4,000 IOs. The sort cost for table S is 2,000 IOs, right? But then the merge cost is just, again, scanning of the pages that are sorted once, and that's down to 1,500 IOs. So the total cost is now to 7,500 IOs. So in the case of everything's in memory, that was 150 milliseconds. Now we're down to we're at 750 milliseconds. And then we can still spell to disk if necessary. This is starting to look pretty good. I've already mentioned this now, but the worst case scenario for us, or pretty much all the join algorithms, is that you have the two tables you're trying to join on, they have one value for all the tuples. In that case, there's nothing you can do to make that work well. It's like, the worst case scenario. But in general, data doesn't usually look like that. Now, you wouldn't have a billion tuples that everyone has the same birthday, and you want to join these two tables. Like, that doesn't happen that often. Or at the scale where this would be a huge issue. So again, as I already said, sort merge join is going to be good for us when the data is already sorted on the join key that we want, or the output of the query, the final output there's an order by clause that's also on our join key. Because again, we can just do the sorting for either both the join and the final output, and we don't have to do it as a separate step. Right? Yes.
So the merge cost plus n is the best case scenario, right?
Yes. The statement is, and they're correct, the merge cost, going back here, of m plus n is the best case scenario. Yes, with no backtracking. All right, so let's jump into the good one, the hash join. So the basic idea is, again, we have a tuple in R, we have a tuple in S, we want to join them together. And the idea is that we're going to use the hashing mechanism, the hash function, as a way for us to find that the matching tuple from one side versus the other, right? And we can base it on this nice property of the hash functions, is that given the same key, it'll produce the same output, the same hash value. So if my join key is the same as your join key, we want to join together, then we'll end up hashing to the same location in either a hash table or a partition, right? And in the same way, when we talk about hash tables of like a way to take a hash, you're sort of randomly jumping into a linear array of slots, where we may have to look around to find the data we want, because we have to sort of scan through till we find the slot that has the data we want, or an empty slot. The idea is the same, as that with hashing, we'll land in a location where the data that we could have a match, if it exists, will be nearby, and therefore we're not having to do a complete linear scan of all the data, or sequential scan of all the data, as we did in nested for loops. So a basic hash join algorithm on a single node has two phases. First phase, we're going to do a sequential scan on the outer table, and then build a hash table using some hash function. And then the second phase, we're going to scan the inner table, use that same hash function, look up in the hash table to see whether we have a match on our join key. So we can use whatever our favorite hash table we want that we discussed earlier in the semester. In practice, most systems are going to use linear probe hash table because they're so simple and so fast. Even on a distributed system, it's going to work pretty well. And then inside the hash table, we'll have to at least include this is where we at least have to include the join key, because again, we may hash to some location that may have an entry, in that slot, but because the hash functions are not guaranteed to have collisions, we have to then still do a comparison of the join key to say whether we have what match or not. So the basic join algorithm looks like this. We have 2 for loops still, but they're not nested anymore. They're just separate and executed in serial order. So the first thing I'm going to do is allocate some memory for some kind of hash table, scan through the outer table, or what we call the build side of the join, use the hash function, populate the hash table, then do a sequential scan on the inner table, also called the probe side of the join, scan through, probe inside the hash table, see whether we have a match or not. All right? Pretty basic, but works really, really well. Because again, it's basically divide and conquer. I'm taking what otherwise would have been a sequential scan and narrowing down the scope amount of data I have to look at, because I'll land in my hash table and find the thing that I want. Now, obviously, I want to make sure my hash table is appropriately sized so that I'm not doing the worst case complete sequential scan of all the keys if my hash table is too full. But in general, this is going to work really well. Yes? The question is, what is the difference between this and an index nested loop join? Nothing at a high level. Index nested loop join has an existing index, and I use that. This is I'm building the hash table just to do the join. Most indexes in real systems aren't going to be hash tables, though. Most, like if you call create index by default, most systems, nearly all systems, you'll get like a tree, a B+ tree. And so the B+ tree is great. It is the most important data structure in the world, but it's not going to be the best thing for joins, for doing a lot of joins. Because if my hash table is large enough and I don't have a lot of collisions, then I'm doing O1 lookups. And for a billion tuples, that's a big deal. Right? That's going to be a huge difference in performance versus the log n traversal in a B+ tree. So one easy optimization we can do to make our hash joins go faster is to actually build a Bloom filter as we're populating the hash table. And then now when I want to do my probe, I check the Bloom filter first. If there's a match, then I probe the hash table. Otherwise, I don't probe the hash table. Right? So this is sometimes called sideways information passing. Some systems will call these Bloom joins. All right? The basic idea is all the same, even though it has different names. So say that now I'm going to build my hash table on R. Right? This will be the build side. So as I'm scanning through R, I'm populating the hash table, but then I'm also going to be building a Bloom filter. And then now once the hash table is done, and now I want to start scanning S to do the probe into the hash table, I'm basically going to pass along the Bloom filter over to this guy and say, hey, before you check the hash table, go check the Bloom filter. Because the idea is that I still have to hash anyway to probe into the hash table, but then landing the hash table and then doing the scan and doing the key comparisons, that could be rather expensive. Versus doing the Bloom filter lookup, that's way faster. So this is great when my join predicate or my join keys are very selective, meaning most of the tuples I'm examining aren't going to match on the join, and I'm throwing most of them away. Then this is going to be a huge win for us because doing a lookup on the Bloom filter is super cheap relative to the hash table. So this is a weird thing for kind of violates the notion of in our query plan where we're sending data up from one operator to the next. Because we're taking information that we collect on R and having this side channel thing we pass over to S. But again, the win is going to be quite significant. In really selected joins, this can be like a 2x performance improvement for just building the Bloom filter. All right. So the example I showed before for the simple hash join was kind of like the naive nested loop join, where you assume everything's in memory and kind of rip through it. But if everything's not in memory, then we need to be able to still be able to handle that. And we don't want to maybe build a giant hash table for to do our join, because the hash table is not going to fit in memory. And now we're doing random IO to different locations or different slots in that hash table. And that's going to be terrible for us for performance. So we're going to rely on, and again, that same divide and conquer approach, where we're going to split the data set we want to join up into smaller subsets and potentially build hash tables for those smaller subsets that do fit in memory, and then rip through that very efficiently. So this idea goes back to the 1980s. I think the textbook calls them partition hash joins. Sometimes you'll see in the literature they're called Grace hash joins. And this is named after a seminal work in the 1980s out of Japan, building this database machine called Grace. And they had a paper saying, hey, look, we have this great database machine called Grace, and here's the hash join we're using. And so the Grace database machine obviously no longer exists, but the legacy is this hash join that pretty much everybody uses today. So the other algorithms we talked about is kind of two phases. We have the partition phase. We're going to go through both tables, hash the join keys, and then divide it up into partitions and the buckets. And then in the second phase, for each partition level, we're going to again scan through the data and just do the simple hash join that resides in memory that we saw before. Who here has heard of the term database machine before? Probably nobody, right? It's basically specialized hardware that people built for specifically to run database systems. This is why database systems are the most important piece of software. Think of like, other than, crypto stuff he was doing, like other than people building specialized hardware for crypto, or maybe like, graphics and things like that, or machine learning, people have been building specialized hardware for databases for a long time. So this is one of the earliest ones from one of the early days called IDM. I just like this picture because the guy's like in a suit working on a database. This is what the future was going to look like. But they were building specialized hardware to do sorting in network as well. And this was 1980s. That company's obviously no longer there, but there's a bunch of companies around today that'll sell you database appliances instead of calling database machines, called appliances, that again are customized hardware or tuned hardware to run database, database workloads. The most famous of these is probably going to be Oracle Exadata, and then the Teradata stuff, right? We're thinking of like massive data warehouses. Each one of these racks is like $5 million, right? And then maybe double that now. But then you pay $1 million a year for support for this. Like this is what you would run on, like for high-end workloads. And inside this, on like Oracle controls all the hardware and the OS. They'll have like I think FPGAs and things like that inside this make it run faster, right? One of the companies that will be giving a talk with us in a few weeks is called Yellow Brick. They started off selling a database appliance. Again, thinking like specialized hardware customized for running a database workload. And this is, they still make a lot of money doing this, right? Anyway, so like just goes to show people are trying to do specialized hardware for database for a long time. Now the current trend is to see how we can leverage GPUs. There's a bunch of companies that have been doing this for about 10 years now. We had a seminar series in 2018 where a bunch of the GPU database vendors came and gave a talk. Obviously they're competing against getting GPUs from the ML AI people, but there's a lot of like, one generation older GPUs that people don't want to use for training anymore for ML stuff that you can still use in databases and run efficiently. We're not going to talk about GPU databases in this class. That'll be in the advanced class. Let's just say that people have been trying to do this for a while, but it doesn't always pan out. Part of the reason why the database machines in the 1980s didn't really pan out either is because in the early days of computing, like by the time it took you to design specialized hardware, fab it, and then ship it to customers, Intel or Motorola or whoever was putting out new CPUs, there were pretty significant jumps in performance because of Moore's law, and the performance benefit you get from specialized hardware just sort of was negated pretty quickly. Nowadays, unless you can get it on Amazon or in the cloud, people don't really care about running specialized hardware because you want everything to be sort of commoditized. Anyway, Grace hash join was an early days machine, and there's a lot of work done in the space. It's the holy grail for databases. Like if I have specialized hardware to run my database system and run faster, that'd be fantastic. No one really has seemed to sort of crack that nut yet. Okay, so the way partition hash join is going to work is sort of like that partitioning phase we saw when we talked about aggregations last class. So I'm going to scan through all the table, my outer table, use a hash function, put everything into buckets, right? Scan everything on the inner table, same thing, put everything in buckets. And then now I'm going to be able to spill these out the disk if my buckets get too big. But then now when I want to do the sort of the second phase of do the join, I only need to examine the data within one bucket and do that comparison across the two tables within one level at a partition. Because I know that there isn't going to be a key that got hashed into partition 0 at the top for R that's going to get hashed into this bottom bucket down here. Because the hash function doesn't work that way, because it's the same hash function, the same value, they'll end up in the same level. So then now when I want to do my probe to do the join, I'm going to do one level at a time, bring those pages into memory, build a hash table for that, then at the same level, read all those buckets from the outer table, S, and then do hashing to this hash table. Just again, now everything's in memory, find my match, produce my output. And then once I'm done probing on the S side, I throw the hash table away because I don't need it anymore, because there's never going to be another match at any other level. And I just do the same thing all over again. Yes?
How are the buckets, I guess, like, are they, like, how do you choose the number of buckets that you're gonna have? Like, would you be, like, would it be, like, kind of, like, page in terms of, like, the number of buckets?
So the question is, how do I choose the number of buckets I have, and how do are they just pages? They're just pages. I'm just appending to them, right? And then the size is determined by the database system, either through a parameter that you can control as a human, like the operator, the administrator. So you can tell, like Postgres, like you're allowed to use 1 megabyte of memory to do hash joins or something like that, right? So someone is telling you how many pages you get to do this, right? And then if the system decides that's not going to be enough, you do recursive partitioning. We'll see that next. Right, memory is finite, so I just can't say I'm going to use all my memory. Something up above is determining how much resources you have. Yes?
Why does this produce like a complete join? Because you could have rows in one bucket that could join with other rows in other buckets.
The question is, how is this producing a correct join, not a complete join, correct join? Because your statement is, because you could have rows that in one level partition, you're saying match to another level? That can never happen, right? Because if the join key on table R and table S, if they're the same values, when I hash them, same input to the same hash function because it's deterministic, will produce the same output. I mod that by the number of whatever, K here, tell me how many levels in my partitions I have. They're going to end up at the same level always. If they don't, then something's wrong with the hardware, and the data system can't handle that, right? But it's like the sort merge stuff where, like, because I've sorted the data, I know I can't see something that I should have seen earlier down below because it's been sorted. If my sort algorithm is wrong, then I have a bunch of other problems, right? So if my hash function is acting all weird, then you're in trouble. But in general, the algorithm will work. Yes?
Well, if you have, like, all the same, like, join attributes, would they, like, do they still have, like, the same number of buckets? Like, theoretically have something on a different level.
So you're asking, what if I have, I think basically, what if these buckets get too full? Yes, next slide. Okay. So if the partitions don't fit in memory, which they were asking about, then I can just recursively partition this again. And again, if everything still doesn't fit in all memory, I partition it again. Now again, in the degenerative case, if all the values are the same across all my keys or all my tuples, then recursively partitioning doesn't do anything for us. But again, don't do that. At the end of the day, there's nothing you can do. There's no algorithm magic to make that go away. So eventually I'm just going to keep sub-partitioning my partitions until they fit in memory, and then do my join. In practice, you only had to do one extra level of recursive partitioning in real systems. Again, if it's a degenerative case, there's nothing you can do. But then if you identify that you're going to have a lot of keys that are going to be values of the keys are going to be the same, then you just fall back to do the block nested loop join. Or if my partitions are actually going to be small enough, I don't maybe want to build the hash table. We'll see in a second. I'll just do the in-memory nested loop join, because that's going to be really fast to do as well. So let's say this is the table we want to partition, right? We have a bunch of buckets, k minus 1, and then say for whatever reason a bunch of the keys are hashing into the bucket in level 1. So I think of this like just every single time the page gets full, I write out the disk, I make another page. So I'm keeping track of the metadata of how many pages I have at each level. So there's some threshold to say, okay, this thing is getting too full, everything is too skewed. So then now I'm going to do another round of hashing, pick another hash function, or take another seed for the hash function I'm using, and just partition the data at that level all over again into a bunch of more pages, or a bunch more buckets. And then for the ones that weren't too full, I just carry them along at the next phase because I don't need to repartition them. I don't care about them. So then now, as I do my scan, the same scan on the inner table, if they hash to the two bottom ones, that's fine. I don't think anything special there. And then now I just do my in-memory hash join as I did before. But if I recognize that if I'm hashing to one of these ones that got overflowed, then I know that I need to call the second hash function to hash them again, and then now they'll land up and align with the keys coming from the outer table. So just like the index probe cost in the index nested loop join is hard to quantify, recursive partitioning is also hard to quantify because it depends on the key distribution, right? So in general, we're just going to say to estimate the cost of hash joins is going to be this formula here. So 3 times n plus n, right? Because it's 1 scan in for n plus n, write it out, and then 1 scan back in to take the partitioned buckets and then do the hash join. And everything's in memory at that point. So using real numbers, now we can get our example table before down to 450 milliseconds. So sort merge join was 750 milliseconds. In-memory nested loop join was 150 milliseconds. But if I have to split a disk in this case here, I can get it down to 450. So that's pretty good. So one semi-easy, but not always easy to implement, difficult to get right optimization is use what is called a hybrid hash join. And this was something that was invented early 1980s as an extension to the Grace hash join stuff. And this was invented by the other database professor, Janesh Patel. His PhD advisor invented this, I think with Jim Gray, one of the Turing Award winners in databases back in the day. And so basically what happens is if you recognize that a bunch of the data, if your data is skewed and a bunch of the tuples are all going to the same partition, you'll just keep that partition in memory, spill all the other ones out the disk, and then just do an in-memory hash join or in-memory nested loop join for that hot partition, and then just do the regular Grace hash join algorithm for the other partitions. Right? So again, assume we have, for whatever reason, all the keys are hashing this one here, right? So I would recognize, okay, this thing's to be hot, so I don't want to maybe spill out the disk. If it's not that big and I can keep it in memory, let me go ahead and just do that. So I would keep this level in memory, take all the other ones, spill those out the disk. And then I just take now, while this is already in memory, build the hash table for this, maybe not even do the bucketing right phase, just switch it directly to the hash table. And then now populate it as I'm scanning along. And then this guy can then do the join directly against it. Right? I think it's called hybrid because, again, instead of doing the hash table part at the top level here, you could just do the nested loop join because it's already in memory. So you're kind of doing both algorithms together. This is a challenge to get right because, like, again, how do you know whether something's going to be the hot partition or not? All right. Are you just better off using the extra memory to keep these things, keep more of these pages in memory rather than building this hash table thing? So Postgres does this. A bunch of different commercial systems do this. The language is confusing because sometimes they'll call this the hybrid join instead of the hybrid hash join. So finding out who actually does this is not always clear. And like I said, sometimes it's just better using the buffer pages for the partitions you're building, rather than specializing one of them to be the hot one. All right, so finish up. So for our hash joins, the probe table can be sort of really any size, but in general, we want it to fit in memory because again, we don't want it to do a bunch of random I/O on disk. That's going to be the death to us, right? If everything fits in memory, then the probe can be really fast. You just sort of scanning through once and don't do any partitioning. If you don't know what the size of the table could be, then you maybe want to use the extendable hashing, or the linear hash table that we talked about a couple classes ago. Most systems don't do that because, again, those data structures are less efficient because there's more machinery to them than like a linear probe hash table. So when we talk about query optimization, as I said a couple times already, that like they're going to try to estimate how much data or how many tuples you're going to have to put into your hash table so that you can sort of size it correctly and not have to spill or resize it later on. But getting that correct is going to be super hard to do. It's hard enough to do it for base tables themselves, like if I'm reading the tables, but then try to do estimates of the size of data after I do multiple joins. Everyone gets that wrong and horribly wrong. So, it's the only way to sort of to handle it is to be very, you over allocate the memory for your hash table to avoid that problem. Of course, that makes you less efficient because now you're using memory that you're allocating memory you may not actually need for your hash join, could be used for other things. But again, you're just trying to avoid having to spill to disk. All right, so here's a summary slide of the different algorithms we talked about. Again, in general, the hash join is going to be preferable, right? If you don't already have an index and you don't think the data you're trying to join it will fit in disk. Yes.
You made comments on whether we have index on R, if the table is sorted on R,
Yes.
or if the join is sparse, so you need to filter. So
Yes.
does a database system maintain multiple join algorithms, and does one of these?
So the question is, I mentioned a bunch of different scenarios where one join algorithm will be better than another. And so the first question is, do database systems implement different join algorithms? Yes. Do database systems then try to figure out which of these join algorithms they should use at runtime when your query shows up? Yes. So that'll be query optimization. That'll be after the fall break. Roughly the formulas they're going to use to try to figure this out looks like this. Right? Now,
What are the common ones that are there in a database system and they try to switch between them? For example, they won't have naiveness. So what are the ones that they would actually have?
so the question is, of this menu here, which ones are going to have? The good ones have all of them. Postgres has all of these, right? Oracle has all of these. DB2, DuckDB, you have to have all of them. MySQL didn't have hash joins until like, 30, 25 years later. Like they didn't add it until 2019. And I don't think they don't have submerged joins still, right? But that's okay because they're focusing on like not analytical workloads. It's an OLTP system, right? So I was just trying to say like if you're building a data system from scratch, when you have to implement your join, the first thing you're going to implement is basically a block nested loop join because it's the easiest thing to do. And then after that, you're probably going to implement the hash join because it's going to be way more efficient. And there's a bunch of different optimizations and tweaks you can do for all these. Like there's a bunch of variations of these things. You can have different hash tables, based on the data you're going to join together. Like ClickHouse has 20 hash table implementations. Like within these general categories of algorithms, there's a bunch of different optimizations you can do. And that's going to be what distinguishes the enterprise expensive systems from the open source ones. Now, with that said, DuckDB and Postgres have a lot of these things that they're pretty good. DuckDB is probably pretty state of the art, right? But the challenge is also going to be in the query optimizer to figure out which of these one of these ones you should use. And in practice, again, I said the estimations are always going to be really bad, so the hash join is usually the fallback. Yes. The question is, what's the C in index and loop join? That's the constant cost of probing the index. Undefined because it depends on what the index is and what the data looks like, right? It also depends on like what the join is. If it's equijoin, in the case of a B+ tree, it's log n to go to the bottom. But if it's like they were asking, well, actually, and if the key is not unique in that index, I may traverse the bottom and then scan along the leaf nodes. How many do you have to scan? Well, it depends on what the data is and what the query is. So that we just say C. But when we talk about query optimization, it'll know, at that point, you'll know what the query is, you know what you want to do, you know what the data roughly looks like, you know what data structure you're hitting up. So that query optimization time, when you take a SQL query and convert it to the actual plan you execute, that's when you fill in C. All right, again, so the main takeaway from right here, it should be hashing is almost always going to be preferable to sorting. Unless the data needs to be sorted as part of the output, then you can just piggyback off that. Even then, in some cases, sorting that, doing the hash join, then sorting it still might be even better. Again, it depends on the hardware, depends on the query, depends on the data. So, and related to his question, the good systems, good in quotes, will have pretty much all of these techniques and a bunch of other optimizations. But these are the general 3 algorithms you can do. You can either have nested for loops, hash things, or sort things. There isn't anything else. Okay? All right, what's next class? Yeah, midterm. Okay. So again, make sure you have your notes, your CMU ID. Don't do any weird things. Like one kid brought his wet laundry. Don't do that. Right? I won't be here, but my PhD students will be managing things for us. Okay? All right, man. Hit it.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.